Imagine you're in a self-driving car, and the road ahead has a strange new sign, a shape the AI has never encountered. How does it figure out what it is? That's the core challenge this research tackles, teaching AI to understand 3D environments, like LiDAR scans, even when faced with the unknown. Let's break it down. LiDAR sensors generate a 3D point cloud of the world, capturing millions of data points that form a digital sculpture of the environment. But labeling these points, identifying which are cars, trees, or pedestrians, is a mess. Traditional methods rely on 2D image models, which is like using a blurry photo to paint a 3D statue. Details collapse. Enter vision language models, VLM, the same tech behind AI assistance and image search. These models see images and understand text, making them ideal for open vocabulary tasks, recognizing objects they've never seen before. But here's the catch. VLMs are trained on 2D images, not 3D LiDAR data. So how do we bridge that gap? The answer is LOSC, the LiDAR Open Vocabulary Segmentation Consolidator. Here's how it works. Step 1, from 2D to 3D. A VLM analyzes camera images and uses text prompts like a bicycle or a traffic cone to guess labels. These labels are then projected onto corresponding LiDAR points, creating a rough 3D map. It's like sketching a statue from a photo, then filling in the blanks. Step 2, cleaning up the noise. The initial labels are messy. LOSC fixes this with 3 smart steps. Robustness to changes. It filters out labels that flip when the image is flipped or adjusted, ensuring consistency. Time-based consistency. It checks if the same object stays labeled the same across frames, like a car staying car as it moves. Iterated refinement. The model trains and retrains itself, getting better with each round, like a student practicing a skill. Step 3, the final 3D model. After cleaning, the refined labels train a 3D network to accurately segment LiDAR data. The result? A system that's not just better at recognizing known objects, but can adapt to new ones, like a never-before-seen road sign, without explicit training. Now let's look at the data. Researchers tested LOSC on datasets like nuScenes, which labels every object on the road. But not all labels are equal. For example, car has over 100 million labeled points, while trailer has just 1.3 million. Why the gap? Some objects are rarer or harder to spot, like construction vehicles or traffic cones. Here's where it gets interesting. AI models were trained across 3 iterations, improving accuracy measured by IOU, intersection over union, a scorecard where higher numbers mean better object recognition. For car, the score jumped from 70.5% to 77.3%, showing the AI gets better with practice. But not all classes improved equally. Trailer stayed around 12%, likely due to limited data. Meanwhile, vegetation hit 81.2% by the 3rd round, thanks to better text prompts like tree or bush. Some labels were flagged. Yellow highlights points that didn't meet criteria, while green shows labels selected via special rules. The Sup column reveals models trained with perfect ground truth labels like human experts, achieved 96.9% accuracy for drivable surface. But real-world data is messy, so the AI has work to do. So what's the takeaway? LOSC proves that combining 2D VLMs with 3D refinement unlocks open vocabulary AI. It's a step towards smarter machines that navigate our complex world without needing to see everything first. Next time you see a self-driving car or a 3D map, remember, behind the scenes, AI is solving puzzles we once thought impossible. Thanks for watching. Stay curious. If you're curious about how these findings apply to self-driving cars or AI systems, hit that subscribe button for more deep dives. Drop a comment. What's one thing you'd like to see explained next? Until next time, stay curious.